box, same magical box that appears in most of the lectures on a floor. Point A, which is 0.5 meters. 0.5 meters. And what the weight of the box is 100 Newton. And what force P being applied at point A at, no, it's just, sorry, 10 Newton. That's 10 Newton. Sorry, 100 Newton. This is 10 Newton force applied. That's another reaction force of 100 Newton. And this is the, what you're telling me, that there is a 10 Newton friction force. Because of this applied 10 Newton. The object is in equilibrium, so it means that the friction force is equal to force P. Clear? No issue?
Yes, sir.
So let's do sum of all the moments along Y. That's 100 minus 100, which is 0. So basically it's this one and this one, okay? So no issue. According to you, there's no issue. Then we do sum of all along x-axis. So that's P, which is 10 Newton, minus that's friction, which is 10 Newton in the opposite direction, that's 0. According to you, that's no issue. So let's take moment at A. Moment at A. So that is 0.5 multiplied by 10. So that is 5 Newton meter. And that is clockwise. Am I right?
Yes, sir. Look.
So the resultant moment at A is clockwise. So why the box is not rotating?
So,
come on, you're engineers. Don't know how to take moment at a point? Okay, let me explain what moment is. Let me explain you what moment is. Let us go back to class 6. That's distance D and that's force F. So moment at point A is force into distance. That's the force. This is distance. Is that clear, or do you want to go back to class 6 then? Is there an issue here?
no, sir.
Okay,
No,
good.
sir.
So that's good. So now tell me, I'm taking moment at point A, but it's in equilibrium.
Sir, it's an unstable equilibrium.
Unstable equilibrium. So it's moving, eh? The box is moving.
No, sir. It will. The box will tend to tip over.
Tend to tip over. So it's moving. You got unbalanced force. Let me explain what unbalanced force means. If you've got a box on a perfectly smooth surface and you're applying a force of 10 Newton here and you're applying another force of 9 Newton here, and there's frictionless, it's on a frictionless surface, so it means 0. Will the box move in this direction?
Yes, sir.
Yes,
sir.
because you do sum of all the forces along x, which is now 10 minus 9, which is 1 Newton, and the resultant is 1, so it moves. So come on, tell me,
सर एक्चुअली जो फ्रिक्शनल फोर्स है ना यहाँ पे वो नीचे वाले से बैक कर रही है बजाय उसकी साइड बैक करने के, तो इसलिए टॉर्क तो भी पैदा हो नहीं सकता, मोमेंट तो पैदा होगा ही नहीं.
That's something new.
So maybe the base is large enough to resist.
Maybe.
the moment.
I guess maybe the temperature of the room was too high, or maybe humidity was a bit low, or maybe the box is not square. Don't go for maybe. And there are a lot of assumptions. Okay, so tell me, friction is always opposite and is parallel to the surface. So the force of 10 Newton friction will remain there.
Sir, maybe friction.
Maybe.
Friction.
Yeah.
Forcing a reaction.
Say again? That's interesting. Say again? Didn't get that. Watch carefully what I'm going to do. Come on. Can you take a moment now at point A for me, please?
It would be 0.
Isn't that magic?
You shifted the positions of the action and reaction force. Like,
Yeah, I cannot shift it. It practically happens.
okay. So they're not on the same axis anymore.
Yes. Why did you assume it's on the same axis? Assumption is the mother of all disasters. That's why I'm on assumption. So what happens when I do this? Now tell me.
The position of the 100.
What happens to this distance?
Sir, it will become 0.01 meters.
0.01 meters. Interesting. So you're telling me this reaction force
0.0.
is
So
moving.
0.01 sir, or like 0.1.
0.1.
So you're telling me this reaction force is moving. Interesting. What about this now? And what will be the distance x?
Zero point 0.02 meters.
0.02
meters.
meters. It was 0.01 and then it was 0.0.
True, sir. 0.2.
So it's 0.2. Okay.
Yes,
So this
sir.
is 0.1. Am I right now?
Yes, sir.
Yes.
Okay. So can you see what's happening? As I increase P, box doesn't move. The friction force increases. My reaction force R is moving to the right.
Yes, sir.
Okay. So if I keep on increasing P and the box doesn't move, there will be a time when this R will come to this soil. Let me get rid of this is soil. This is my friction force. I'll write it here. There will be a time when my R will come here and this becomes my X. Am I right?
Yes. Yes, sir.
Can I bring it to this edge? By increasing P, the object doesn't move. So the P increases, my friction increases. Is that right? If the object is not moving, I increase P, the friction will increase with same amount. Is that clear?
Yes.
Yes, sir.
Okay. So as I increase P, friction increases, the displacement of R also increases. It moves more to the right. Clear?
Yes, sir.
Yes.
And this happens
Yes,
to balance the moment. Clear? Now, what happens the moment R tends to move outside the box? What do you think what will happen?
Now the box will tip over.
Yes, you're absolutely right. So what I'm want to tell you that as I increase P, friction increases. Condition is the object is not moving, but my R will be moving to the right. The moment R reaches the edge of the box, that is the tipping moment. The box will tend to tip over. Is that clear? It will not slip. It will tip over. Is that clear?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. So this is what we are going to go through now for we'll go through now the text, and let me explain another phenomena here. Okay, again another same magical box. Oh, come on. It's on the floor. I apply a pressure P here. Force, so force. It is 100 Newton. Reaction is 100. I'm writing the reaction from far away because I'm not interested in I'm not considering the movement of R. I'm just taking X and Y axis at the moment. So, so if P is 1 Newton, my friction is 1 Newton if the object is not moving. Okay, so I'm assuming the object doesn't move. Okay, so if I increase to 10 Newton, what will be my friction?
10 Newton.
10 Newton.
10 Newton. Okay, so you can do the same. You can do it practically also. You put a thick book on the table and you try to force it from one side. Put very little force, the object will not move. Am I right? If you have a box on the table, if you got a book on the table and you want to, you apply a force in the x-axis, very little force, the object will not move. You agree with me?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So you keep on increasing the force. There'll be a moment when the object will start moving. Is that right?
Yes, sir.
Yes, sir.
Yeah. So that what we call is limiting coefficient of friction. I'll talk about that. Which means that as you increase the force, your friction increases. But there is a limit to this friction force. Let me give you a simple example. If I have this box on a concrete ground, okay, rough ground, I increase the force slowly from 1 to 100 Newton. I'm increasing the force P. At some moment, at some time, at let's say assuming around about 55 Newton, the object will start moving. Okay? So I've got a maximum friction force of 55. If I do the same on a glass, I put the box on the glass. On the floor, it moved at 55 Newton, P is equal to 55 Newton force. On the glass, will it move at 55 Newton P force or well before that, less than 55?
Sir, less than 55.
Less than, because it's a very smooth surface.
Yes, sir.
So what has changed? That is the contact between the two bodies. And that's what we call coefficient of friction. Depends on the contact of two objects. So now let's go through the lecture slides and everything will get more clear. Okay, so yeah, I've already explained you. Body friction force equals speed. And as the force increases, your N is shifting. Can you see that? I will explain this again in the coming slide. Let's move on. Okay, experiment shows that friction force acts tangent parallel to the contact surface in the direction opposing the relative motion or tendency for motion. A box on a floor, I've got P force here. The friction force will be tangent to the surface, parallel to the motion, opposite to the motion, but parallel. Okay, that's what it says here. Okay, so again, interesting one. I'm looking at this one, okay? I've got force, I'm applying P. Now this is telling me come on. So let me make a graph. Come on. Let me make a graph. And I'll put here, well, I'll put time here. Yeah, let's put time just to keep things simple. It's time, okay? Sorry, this is time. In layman. And this is P force. So I'm looking at this one. So if I apply, I'm applying constant force. I will increase the force from 1 Newton to 100 Newton. Okay. And the object is on the ground. I'm not looking at this and this. Just concentrate on the box here and on the graph that I'm drawing. And the graph shows P and time. Now I'm applying a uniform rate of force. So So this is my force applied, okay, force. So I'm applying force, that is 1 Newton, 2 Newton is going up. The object will not move. Okay, there will be a time that object will start moving. And if I put any further P, then P will not increase because the object has started moving. Okay, so again, if I keep on applying force, there will be a point where P will not increase any further because the object will start moving. Will that happen?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, and this is the point just before the object moves. That is your P value, and this will be your maximum friction. Maximum friction, and we also can call it static friction, maximum static friction or limiting friction. Static friction. So let's look at the diagram. It will make more sense. Okay, so what it says here, you got the box, you apply force, same thing happens, remember? And as you apply force, the force is increasing, the friction is increasing, your P is increasing, your friction is increasing. Same here. Remember, your P increases, your friction increases, provided the object is not moving. At this point, the object is at the verge of moving. This will be your maximum friction force. That's a maximum static friction force. And once the object starts moving, your friction force gets constant and you get a straight line. Your friction force now has reduced, and this what we call is kinetic friction. Why this happens? It's very simple. If I put a box on a floor, let me magnify this contact area. So the box surface would look something like this. It's rough, always rough. And the floor surface will also look like this. Okay. Now they are making contact, sorry, it's a contact. So they are making contact, okay. Okay, so they are making contact. Now you can clearly see here that there's a lock. You've got trough of the box crust, and you've got trough of the floor also. So you can well imagine they are locked. So when you apply more and more force on the box, they are locked at these points. And once it lifts and starts moving, then it kind of hops over those asperities. And therefore, you see a maximum friction force. At this point, the asperities get unlocked and the object starts bouncing on them, and the friction goes down and stays down, because now the box and the floor is kind of micro bouncing on it. Is that clear?
Yes, sir.
Yes, sir.
So an object, again, do it yourself, put a book on the table, try to apply force in the horizontal direction, it will not move. There'll be a point when it starts moving, and you can, well, I would suggest put a heavy thing on the table and apply a force slowly, so you will see that the object will not move. There will be a point when you will be applying maximum force, and after that, once the object starts moving, you will feel that the applied force has reduced. Clear? So,
Yes, sir.
Yes.
to study the characteristics of friction force, let us assume that tipping does not occur S is small, then we gradually increase the magnitude of P. Typically, the experiment shows that the friction force varies with P. I've already covered this. The maximum friction force is attained just before the block begins to move. We call the situation as impending motion. The maximum friction force is attained just before the block begins to move, just before the block begins to move. The value of the friction is found using F equals mu s, where mu s is called the coefficient of static friction. The value of mu s depends on the material in contact. I'll show you that. Once the block begins to move, that is after this point, to move, the friction force typically drops. You can see that was the highest friction, and it dropped to this level now. So once the object begins to move, the friction force typically drops and is given by kinetic friction, that is Fk is equal to mu k, and the value of mu k, coefficient of kinetic friction, is less than the coefficient of static friction. Okay, and same thing is here, and this is the point. Sorry, this is the point where you get maximum static friction, and once it starts moving, you get your kinetic friction here. No, I won't cover this. I will stay here. I will stay here. I thought there was static friction. Hold on, where is it? Yeah, coefficient of friction. Okay. So this is mu s, static coefficient of static friction. So when you got aluminium on steel, the coefficient is 0.6. If you got concrete and on rubber, the coefficient of friction is 1. If you got glass on glass, the coefficient of friction is 0.9. If you got steel on steel, you got a different value. So it depends on the material making contact with each other. Okay, and it's all about F equals mu s n. What is n? N is basically the vertical force acting on the object. I will explain this in the coming slides. But at the moment, let us go back and spend time on this one here. So, apply force, nothing moves. I'm looking at this one, okay? Apply force, nothing moves. You're keeping on applying P, nothing moves. At this point, object starts moving. This is your maximum friction force. That's the point of maximum friction force, and if F is called Fs. Once the object starts moving, your friction force reduces. That is Fk. Is that clear?
So the kinetic friction would always be less than the static friction.
Yes, right? yes, correct. And the reason I just concept why I did explain, these are disparities, and yes, they are interlocked with each other, and when it starts moving, it kind of bounces on the surface.
Yes, got it.